plan of my talk is as follows. So first I'll take you through some of the avenues of precision calculations, and then along the way I'll just highlight few of the results from my work, and then I will zoom in on one particular aspect of precision QCD calculations, which is basically the next to leading power corrections. Okay. So as we know, the QCD is the theory of strong interaction, and at the hadron colliders, in any study in the hadron colliders, it is inseparable actually. And the reason is that, as the name suggests, in the hadron colliders, the colliding particles are hadrons. And also in the detector, what we see, they are jets. There are many jets. And jets are collimated spray of hadrons. And we know that the hadrons are bound state of quarks and gluons, and their interactions are governed by the QCD. Okay. So every process, be it a Higgs production, a electroweak particle, or top production, quarks and gluons are involved at some level. So QCD is playing a major role in the hadron colliders, not only in hadron colliders, in E plus E minus or in electron ion colliders also, QCD is central. But for today, I will be restricting myself in the study of the hadron colliders only. Okay. So now, why do we need to do the QCD corrections? It is adding like more quantum corrections on the classical object. Let me put it like that. It is adding more refinements on some of the process that we are studying at the hadron colliders. Okay. It is important because it improves the theoretical uncertainties that is huge in the leading order calculations. Also, it prepares the ground to test the standard model at the percent level. Like many of the benchmark processes, like the Drellian production or Higgs production or top production, they have been calculated in very high accuracy, and they are going in like hand in hand in the experimental accuracy. Okay. And to understand the jet formation also, QCD corrections are important, because we, like in QCD, we model the gluon radiation, and through that we can get the information of the jet number, jet energy, jet substructure, and all those kind of stuffs. Okay. And also to improve the background modeling, like in the run 1 of LHC, the main focus was the background modeling of the Higgs production, like the photon at ultimate precision. And without those calculations, it would have been impossible to find the Higgs. Okay. And also it helps in determining many key parameters like the strong coupling, the PDFs, and it increases the sensitivity to rare processes, to BSM processes, which might lead to new physics at some point. Okay. So these are important. Now, this is the evolution of the QCD precision calculations from one of my paper. So as you can see, this is the experimental result. Now, if you do the next to leading order is not put in this figure because that is far away from the experimental result. Okay. So now, if you do the next to leading order result, this is the result, and the uncertainty is almost similar to the experimental level. Now we impose the resummation. I'll tell you what is fixed order and what is resummation in the next slide. Okay. And now we keep on increasing the precision, and this is the ultimate precision that we have got, and we have seen the theoretical uncertainty is much reduced compared to the experimental result. Okay. But this is for particular process, and when you go to the HLLAC, the high-lume LAC, this uncertainty will be much more reduced. So we have to be prepared from the theoretical side that the precision results for most of the important processes, they remain available. Okay. Now let's look at the quantitative part of the precision calculations. So this is the master formula of cross sections, which is the primary object in any hadron-hadron collisions. Okay. So this part is basically the non-perturbative part, which is governed by the pattern distribution functions, and this is the perturbative part. which basically comprises of the amplitude square, the phase space integration, and the average over spin and color degrees of freedom. Okay. Now, I'll be mostly focusing on this part because it can be calculated perturbatively. Okay. And this is a non-perturbative input in this result, but their evolution that you can calculate, that you can improve by perturbative calculations. Okay, and this Partonic cross section that you can write because you can calculate it perturbatively. This is the mixture of the short distance and the long distance physics actually. And you can expand this Partonic cross section in terms of the power of the strong coupling. And this coefficient, they can be determined by using the Feynman diagrams. Okay. Now, let me tell you one milestone calculation in this field, which is the inclusive Higgs production. Okay. Here, few things are important. Look at the timestamp. Okay. From one order to the next order, it took almost decade to go, which tells you that these calculations are not very easy. They are intricated. And also, you see that many groups have calculated the same computation. So that also tells you these calculations are not easy to do. And there are a lot of inaccuracies. And it is always good to have the same result from different groups so that we can say that the prediction that we have made from the theoretical side, they are robust. Okay. And the corrections for this Higgs production, if you look at the LO over the NLO, the K factor is 2. So it is like 100% correction when you go to next to leading order. From next to leading order to next to leading order, it is 20%. And from next to leading order to NQ LO, it is 2%. So, and why that is important? Because it improves the theoretical uncertainties. As you can see in this plot, if you vary the renormalization or the factorization scale that comes into play in these calculations, you see at the leading order, it is not getting stabilized, but at NQ value level, the result is almost stabilized with the variation of the scale. Okay, so that is very important. Now, so all these calculations that I have shown, they are called fixed order because we are taking some fixed term in this perturbative expansion. Okay. Now, let's look at the anatomy of the next to leading order corrections. So basically, it comprises of two parts, mainly the real part and the virtual part. And if you are, as we are talking about the hadron collider, there would be the collinear counter term, which has a collinear origin. And to cancel the single pole, you need to have this term present in the calculation. Okay. Now, NLO is the standard of any processes nowadays. Okay. Anything you calculate it at the NLO level. And the calculation is completely numerical. Okay. For the timing, let's say almost numerical. Why, I will explain. So the real part, so the beauty is that every individual term, they are divergent. But when you sum them up, they give finite result. Okay. And the divergent structure, the infrared structure of this part, they are universal. Okay. So you can subtract them out from the real radiation part and you can calculate it at the integrand level. Okay. Numerically, basically. Okay. Similar is the story for the virtual part, but from the bare virtual part. And as it is bare, and as we have subtracted out two terms, we have to add them up finally, right? And as it is bare, we have to add the counter term, okay? And the collinear counter term is always there. Now, the strategy is like you calculate it numerically, but these terms are simpler. So analytical expressions of these terms are known. So people usually put that analytical expressions and they calculate the full NLO contributions. But we showed that this part can also be calculated numerically. Okay. And that basically completes the calculation of full NLO numerically, completely numerical. This is not a good big deal for NLO because these terms are simpler, but when you go to next to leading order, this will add up actually. And to do this, we have to formulate the antenna, which is basically the sum of two dipoles. What is dipole? I will explain it to you after a few slides. And as you can see, you want to integrate this out, right? Combining. So this is integration over one phase space. This is loop. So you have to use loop tree duality to make this loop integration presentable in terms of phase space integration. Okay. And also you have to find out the integral representation of the renormalization constant. This is a schematic diagram how different terms are interplaying between them to make the cancellation happen. I am not going to the details here, but if you want, I can share it with you. Okay. Yeah. Yes, the last line is also divergent.
And computing numerically means computing the coefficient of 1 over epsilon or something, or what?
We cannot compute numerically, right?
But you said you compute numerically, so I was puzzled. What do you mean?
So that means the divergence comes before the, after the integration, right? So now, when I am telling that I am calculating numerically, that means you have to organize the integration such a way that no divergence come.
So is that, if you organize it as finite or what?
Ultimately, you have to get the finite answer. This piece is finite, this piece is finite. Now this piece has to be finite, right?
Yeah.
You got my point, right?
I'm a bit confused, but so ON plus 1 D sigma R, that by itself, the first line. First line after the equal. Yeah, that one. The first term there.
Yeah.
The first term.
The first term is divergent.
That is divergent.
Right.
But so you added.
Appears after doing the denomination, after doing the dimensional regularization. Right.
So the subtraction term there is divergent.
The subtraction term is there divergent, right?
Okay. And so you added that back, but if you all of them sum together is finite.
Sum is finite.
Okay.
Yeah. Okay, fine. Now there is another avenue which is called the pattern shower in the precision studies. So in the fixed order, what we have seen, we are dealing with limited number of patterns, right? But in the experiments, what we see is the jets, which are collimated spray of hadrons, which are resulting from the multiple QCD emissions. And pattern shower is the approach through which we model the cascade of many soft and collinear emissions. Okay. Now, so basically for a process, it will emit another gluon. So this is the Drellian process. Now in pattern shower, it can emit one gluon from this, two gluon, three gluon, and go on. It goes on like that, right? Now, when you are doing the next to leading order calculation, we have already this part, right? So that means this and this, if we want to match this fixed order calculation with the pattern shower, there is a double counting, right? And we have to remove that double counting. And there are two ways, which are MCAT NLO and Pauheg. And MATGRAPH uses the Pauheg approach actually, which to remove these double countings. And once we remove the double counting, something good happens actually. So you can see this black line is the fixed order calculation. And at the low PT region, it is diverging. Okay. But when you match it to the pattern shower, the result is getting converged. And it is going down because of the Sudakov suppression. Okay. So in the MCAT NLO, I have done many work on these directions. And from the scratch, we have implemented many models so that anyone can do the NLO plus PS corrections in this MATGRAPH MCAT NLO framework. Okay. So this spin 2 I did with Ravi. This I did in my postdoc, and SMEFT I did one work with Shankho. Okay. Now, yeah. So the double counting is coming from the fixed order, there is one real emission, right? And in the pattern shower also there is one real emission. So this is getting double counted, right? These two diagrams. This full diagram is for Parton shower.
So that is because you take the first leg and then you keep showering, is it?
Yeah, same is true for the second leg also, but I am not showing. This is just represented.
No, but this could be in the hard scatter part also, right? This the second and third diagrams could be in the hard scatter. So
exactly.
then it would not be in the Parton shower, I guess.
Yeah, that is what you have to do. You have to subtract out.
That's what you mean.
Yeah,
Yeah,
that's
okay.
what I mean.
All right.
Yeah. Okay, fine. And all these codes are available in this website actually. In this special code section, you will find all our calculations at the NLO plus PS level. Okay. Yeah. Now I said the Partonic cross section, you can do the series expansion in terms of the strong coupling. Also, the same Partonic cross section you can write in this fashion, where this L is large log. And this large log comes when there are two widely separated scale in your problem. Or this could be threshold log. This could be 1 minus the Bjorkenix, many things. Okay. And the first highest term at the alpha is called the leading log. This is the leading log in the alpha square. And when large number is present in the perturbative expansion, that makes the perturbative expansion in danger, right? So to eradicate that, you have to take all leading logs up to all possible power in alpha s. That process is basically called the resummation. Okay. Now let me give you some textbook example how these logs are coming. This is the Drelian production, and if you do the differential calculation of this Drelian production, you get this expression where this Q square is basically the invariant mass of these two leptons at the final state, and S is the energy. Okay. Now this delta function tells you that for leading order it is Q square is equal to S. Same is true for the virtual part, Q square is equal to S. But for real emission, there is one extra emission, and then Q square is not equal to S. Now Q square is ZS. Okay. And Z tends to 1 is basically called the threshold limit. And if you do the calculation, you will find that this kind of logs will appear. Okay. That makes the large contribution in the calculation. Okay. So just to show you how the cancellation is happening, this term you can write it in terms of alternately Parisi splitting function, and when you do the mass factorization, everything get cancelled. Okay. Now if you combine all these three results, you will get the differential cross section in this fashion, which includes one delta function, one plus distribution, and if you allow the next to sub radiation, you will get one log of 1 minus z. Okay. So these first two terms, the delta function and this plus distribution, they are called leading power. And the second term, which is of the form log 1 minus z, that is called next to leading power. Now people know everything about the leading power. They are universal, they are well studied, and resummation is well established. Okay. But for the next to leading power, it is not so well known till now. So it is, first of all, it is suppressed, but it is sizable. It can give 5 to 10% corrections depending on the process. Okay. But no general resummation framework is yet established for these NLP corrections. So that means you have to study these NLP terms carefully so that you can build up the resummation for these NLP terms. Okay. People have tried that. For color singlet processes, many processes have been calculated. Okay. But for processes including jet at the final state, these calculations are difficult. Only one calculation is present in the literature. And the reason behind this is that the process of calculating this NLP contribution, that is very complicated for the jet associated process that I will describe in a few minutes. But we have developed a method which is very simple and through which we have already calculated Higgs plus jet, pseudo Higgs plus jet, and W plus jet, and jet plus jet is underway. Okay. So I'll now describe what is the procedure. Let me first tell you. Yeah.
Either it is equals to one limit. How is that? Why is that?
tell me the question again.
So how can you say that, yeah, it should be singular and the z goes to one limit?
It's not singular.
It's not singular.
But it is giving the large contribution. Right.
But not singular, is it?
Not singular, because this is plus distribution.
No. Before you do the distribution, that you get a singularity, right?
Z, if you put Z equal to exactly 1,
yes,
then there is no real emission.
Huh.
Right. So I want to study the threshold limit, where the energy is just sufficient to.
But is that singular in that limit or not? In Z goes to 1.
It is not singular, but it is larger.
But not singular.
Is larger.
But not singular, is it?
Not singular.
Yes.
Yeah. Okay. Okay, I have explained this. Fine. Now, what do I mean by next to solve? Okay. When you do leading power calculations, suppose a gluon is emitting from the quark lake. Okay. So you directly put the gluon momenta is 0. And there the amplitude factorizes in this format. Okay. And the first, this term is called the Eikonal factor. That is well known. Now, instead of putting k is equal to 0 exactly, I can do the Taylor expansion, what k tends to 0 limit, right? The first term will give you exactly this contribution, and the second term is the next to leading power term. And here the thing is that in leading power, this emission was blind to the nature of this emitting particle. Be it a gluon or quark, it does not matter. The Eikonal factor will remain same. But here you can see the spin information is coming into the picture. Okay, so it is not yet spin blind. Okay, and this is basically called the Lowe's theorem. Okay, and which was basically generalized to massless QCD later by Burnett, Knoll, and Del Duca. Okay. Lowe's theorem tells that when you consider the next to leading power corrections, the internal lines comes into the picture. Actually, you cannot neglect them, the emission from the internal lines. But previously at the leading power, we are not considering the emission from the internal lines, right? No, the order is different. You see, at the leading power, the order is 1 over k. But at the next to leading power, the order is of the order of 1. What? Leading power in the order of k.
Okay. All right.
Okay.
And it comes in only at k squared.
Forget about that. This is the next to leading part, which is of order 1. No, 1 over k is the leading power. Order 1 is the next to leading power.
It comes in only at order.
Yeah, right.
1 over k, there is no such partition.
No. Yeah, exactly. Yeah. Right. Okay. So if you organize all these terms, you will get one scalar term, one spin term, and one orbital term. And if you look at the power, then you square, then you will see the LP contribution comes from the square of this part, which is order 1 over k square at the amplitude level. And the order 1 over k can come only from this contribution, right? Now, people have shown that at the NLP power, after some little bit of algebra, it can be shown that the full amplitude can be written in terms of the leading order amplitude, but shifting the momentum. But the full thing is at the square level. Remember it. Okay. So the canonical approach is that you calculate the leading order square and then shift the momentum. Okay. Yeah. Yeah, that is universal, but for different process, the amplitude square will be different, right? So the shifting is universal, but the terms are different. Yeah. So yeah, see. So suppose one gluon is emitting from So in this diagram, say, one gluon is emitting from the leg 1. It can also emit from leg 2, right? So I am shifting leg 1 and 2. Okay. Okay, so this is the procedure, but the drawbacks of this procedure is that it calculates at the amplitude square level, and you have to symmetrize the square amplitude. What do I mean by that is that suppose you have a 2 to 2 process and you have some term like T by U. So T you can write as 2P1 dot P3, consider everything massless, or you can write it P2 dot P4. Similarly, U you can write it two fashions. So one single term is generating 4 terms. You can see, so this is one of the drawback of this procedure. Okay, and also in the momentum parametration, you can parameterize the momenta in 4 possible ways, and depending on which term you are considering, you have to take the different momenta to make the calculation simpler, which is also not good. Okay, so the whole thing becomes very non-trivial when the analytical form of the leading order squared amplitude is complicated. Let me show you one example. So this is Higgs plus 4 gluon amplitude. It is quite nice and simple. But when you do the amplitude square, this is the form, and the summation is running from 1 to 5. And on top of that, you have to do the symmetrization. So you cannot handle this procedure beyond some point actually. And that is why people could not do further using this procedure beyond photon plus jet. Okay. Now, to calculate the NLP contributions, the next to leading power contributions. In order 1 over k at the amplitude level. Order 1 over k. At the amplitude square level. Yeah. Okay. So now the idea is to use the spinor helicity formalism, and let's see how the things can get simplified. So it is not that people have not done this. People have done this for the gravity, for Young-Mills, and also for QCD. Okay. So any amplitude you can write in terms of square and angle spinors. And when there is an emission, you can write it in this fashion where S0 is the leading power, S1 is the next to leading power. Okay. And there complicated derivatives are coming. Okay. Now the same formula can be presented in a much compact way if you use the VCFW approach. Okay. Which is basically the on-cell recursion. So here the idea is you cut one of the propagator and make it on-cell. Okay. This is the VCFW deformation. And once you do the algebra, you will see that you do not have to bother about the left hand side of this calculation. You just shift 1 and n in the calculation and you will get the NLP contribution. Okay. So here it is written in a more organized way, and I will show you also some examples which will be more clear. So suppose I now want to apply these methods in Higgs plus jet production. Okay. For the calculation simplification, I am using the heavy top mass limit, which makes it a leading order process. And now in this case, there are 2 colored ordered amplitude. Okay. Now I want to calculate, so this is my non-radiative process. I want to calculate Higgs plus jet. Okay. Now this is the radiative process where I want to study what will happen when this G is soft or next to soft. Okay. In this case, I have 3 colored ordered amplitude. Okay. And this is the full formula. Basically, you can separate the kinematics and color always in this case. Okay. Now here the beauty comes actually of this formalism, what we have proposed. So you want to calculate this process when P5 is next to soft. And I have shown you in that case, you have 3 colored ordered amplitude. Now, Now this is the non-radiative process in absence of one gluon. And there, how many dipoles you can make? Dipoles means combination of colored particles. You can make 3 dipoles, right? 1, 2, 1, 4 and 2, 4. And we have shown that to calculate the NLP of this approach, you do not have to bother about this process at all. you can get everything from this non-radiative part, and they have one-to-one correspondence. Okay, so the idea is the number of colored dipoles in the non-radiative part is exactly equal to the number of color dotted amplitude in the radiative part, and that makes the calculation very simple. So yeah.
Like what does that mean? Now you're moving.
Everything incoming I have taken.
So that's shifting of moment. Take momentum negative, is it? Is that what that means? Or?
Yeah, right. Yes. Yeah, so that is a good question actually. So you see, it depends on where the 5 is sitting. Okay.
Right, the radiation.
The radiation. I am going to describe this in the next slide, but as you asked, let me explain. So here see, the 5 is sitting in between 1 and 4. Right. This 1 I can always shift to this. These are carbon.
Oh yeah.
Right. So that when 5 is sitting in between 1 and 4, that corresponds to dipole 1 and 4.
Oh, okay, I get it.
When 5 is sitting in between 2 and 4, that corresponds to dipole 2.
Right. Okay, cool.
Okay.
Nice.
So this is basically the beauty of this approach. Okay, so the new approach is very simple. You form the dipoles. Yeah. Sorry? The name I have taken, yeah, it is similar to Katani-Saimu dipole also. There also you make the dipoles with colored particles only. Yeah. Okay, so the approach is very simple now. You form the dipoles. When the emission is plus of plus helicity, you shift the square spinors. When the emission is of negative helicity, you shift the angle spinors. And that is what I have explained already to Shankho. So here 5 is sitting in between 1 and 4. So now you can get it from the dipole 1 and 4. You just shift the 1 and 4. What I have showed you in the BCFW shifting, right? That's all. I mean, all the color dotted amplitude that will contribute to the NLP calculation that you can get easily from the process where one pattern is less. Okay. All right. And once your method is very simple, you can also find the mathematical beauty hidden in this approach actually. So for example, this is the amplitude for 1 to 4.
So in the previous slide, so basically when you have a radiation, there will be an associate propagator. How can I see that propagator? Like,
you cannot see that propagator. The propagator is already cut using the BCFW that I showed to you, right? This is the propagator.
no, so for the dipole term, let's say there are some divergent propagator. It comes as the prefactor.
Yes, you have nothing to do with the divergence. Okay. These are all leading order processes.
No, so the leading order in the, like, there will be a propagator in the soft and collinear limit. Those propagator will be divergent. If you write the dipole term.
Soft and collinear limit here.
Okay.
I mean, I'll come to that. Just wait for some time. Okay.
Shotajita, very naive question. Can you go to like one of the next few, like when you are showing the amplitudes? Yeah. So just hypothetically, like this approach is only like you have a one-to-one map between these two when we are considering like massless particles, right? Like this won't work for like in principle if we had like some massive radiation which or in a lower energy limit.
Massive radiation.
Like say for example like a W boson coming off. Like I'm not talking about QCD per se.
Okay. If get it. So instead of Higgs, if W is there, W plus Z. I'll describe that.
Okay.
How to do the calculations there.
Yeah, sure. Thanks.
Okay. Yeah. Okay, fine. Yeah. Now as the method is simple, suppose you want to emit a plus gluon from here. Okay. Now for emitting plus gluon, you need to shift the angle bracket according to our method. But there is no angle bracket in this expression. So it readily tells you that all the in image v amplitudes, which is combination of 2 plus and 2 minus, they will not contribute at all. the NLP calculations. That also make the calculation simpler. Okay, so any combination which is of plus plus minus minus, they will be 0. Okay. These are all the amplitudes, just to show you that how compact the results. I am not describing anything. There are also some mathematical beauties, but let's keep it for the moment. Okay, now this is the amplitude as I have explained. This is amplitude square. Now you do the color sum and then you choose any of the parameterization of your choice. No restriction on the parameterization like the previous process, and you do the angular rotating and you get the result. Okay, and the results are very compact also. On top of that, you will see that for any helicity combination, you have 3 terms for this case, like one is D14, D24 and D12. And in this process, we have found that D14 and D24, they are equal to D12. So basically, you have to calculate only the contribution coming from one particular dipole and you multiply it by 2, you are getting the result. So this is as simple as that, this approach. Okay. Now what happens if the emitting particle is,
Securely, can we know that this sum has to be equal to 1?
No, this
If
is,
we have to calculate only, then we can get.
no, this is true for the Higgs plus jet process only.
Okay.
Because there is a dual water identity which holds true for the Higgs plus jet process.
I see.
It is not true for, suppose I am considering W plus jet or jet plus jet. Okay. Yeah. D12 means I am shifting 1 and 2 in the non-radiative amplitude. I have 3 gluons here, right? So I can make 3 dipoles.
So yeah, 1, 2 means what? Like any two of those 3. Pick one or three and just.
No. I have to assign moment to each dipole, right? Because the shifting means I am shifting the. Okay. Let me explain it to you again. Yeah. Here, look at this. So here, this is the non-radiative process, right? There are 3 colored particles. So how many combinations of colored particles I can make in this process? It is 3, right? 1, 2, 1, 4, 2, 4. These are called dipoles. Okay. Now I have to shift the momenta corresponding to 1 and 4, which will correspond to the NLP result. Yes, right, exactly. 1 and 2 spinors I am shifting. Okay, fine. Okay. Yeah. Now what happens if the emission is quark? So this is the amplitude calculation, and after simplification you get this form, and you see this U bar is order root k, because U bar sum to k slash, right? And here there is 1 over k. So the full term is order 1 over root k. Now when you square it, you will get order 1 over k, which is equivalent to the NLP contribution, right? So you cannot neglect this soft quark emission in the NLP calculations. It is not that people didn't know about this. People have done this, but in a harder way. So they have quark operators, and when you really apply it on some process, it makes life difficult actually. So we have shown that only 2 possible combinations, only 2 possible soft quark operator you can create when you are using the spinor helicity formalism actually, and all the rest are 0. So plus quark can couple to plus gluon and it gives you a plus quark. Okay. Minus quark coupled to plus quark is giving you gluon. Okay. All other combination like plus and gluon is minus, that is 0. Okay. So what do I gain from this? Suppose I want to calculate the NLP contribution of this amplitude when this quark is soft. Okay, so this is the full the full amplitude. Now, suppose we do not have this full amplitude, then also I can calculate this contribution when this quark is soft using the quark operator that I have just described. So see here, this Q1 is soft and it can get attached to the adjacent particles. Okay. Now, according to the rule, it cannot couple to a minus gluon, right? So this contribution is 0. Only it can couple to minus antiquark. And then this is our formula, which is matching with the exact calculation. Okay. So just using two soft quark operators, you can get all the NLP amplitudes which will contribute due to the soft quark emissions. Okay. So this is the beauty of this approach. Gauge invariance is maintained actually.
Sorry. Do you choose subsets of graphs so that they are together gauge invariant, or do you just let it go as it is? I mean,
no, actually, I mean, gauge invariance is not hampered because, as I showed, this is directly mapping to the leading order calculations. And
no, not that way. Of course, the whole diagrams altogether will be gauge invariant, but is it possible to collect them in such a way that no, it's not? You don't. Okay.
So the point is that I have shown you the one-to-one mapping. So the radiative portion completely maps to non-radiative part. And there I am not removing any of the diagrams. They have one-to-one correspondence. So gauge invariance is maintained throughout. Okay. So now these are all the processes that contributes to Higgs plus 1 jet. And let me not go into the details. There are really some rich mathematical structures that we have seen. Okay. Now I am coming about the singularity.
Shotri, the last slide, the capital Qs are the heavy quarks.
Capital Q is the quark which are of different flavor.
Okay.
So if it is UU bar, it could be C.
Okay.
Yeah. No, in Higgs plus 1 jet, nothing is soft. But if I emit one extra particle, that could be soft. That is the threshold limit.
So here you have 4 gluons and H. So why is that Higgs plus 1 jet?
Because PP going to Higgs plus jet.
Oh, it's PP. And one soft gluon.
Yeah, one soft gluon. Okay, so now I am coming on the singular part. Okay, so all the logs I have shown, they are of this form, but they are coming with the singularities, and that singularities you can cancel only when you take the mass factorization into the consideration. Okay, so this, how much time do I have? More than 30 minutes. Okay, then I can go slow actually. Yeah. So, yeah. So, we know the alternative splitting function for G going to GG. Okay. This is the format. But when you break it in terms of helicities, this is the result. And if you apply, you will see that this formula is giving exact same pole from what we are getting. Okay. So, there is a complete cancellation, which also give you the confidence that what you are doing is right. Okay. Now, on top of that, there is another beauty, which is, suppose instead of Higgs, which Shankha was asking, I consider W or Z or anything, any heavy particle which is colorless plus jet. If you study the kinematics properly, you will see that the differential distribution comes in this form. Okay. And you will also discover that this coefficient of this NLP log, they are exactly equal to the singular part. Now, this singular part I have already explained, this is cancelling with the mass factorization part, which contains the AP splitting function, and they are universal, right? So, they are universal means this singular part is universal, which means the coefficient of these logs, they are also universal. That is really very powerful statement actually. Okay, so that is what I have written here. For everything.
There will be a color factor, CA goes to CF or something like that.
That maximal color shifting that you have to do.
Oh.
But for off diagonal channels also,
Oh,
like QG or Q bar G, this is true. That we have checked.
okay.
Yeah.
So
Yeah, the reason is that, I mean, if you study the kinematics, you can easily find that this CALL is negative of this pole, coefficient of this pole. And this pole is getting cancelled with the mass factorization, which is governed by the universal terms. So this has to be universal. They are threshold logs. Yeah.
This pole is collinear.
This pole is collinear. Exactly.
It's collinear factorization. It's process independent.
Yeah.
The next are quarks or gluons.
But usually, I mean, like you do, I mean, you always consider the diagonal part. And your resummation is built upon only the diagonal part.
But factorization again is universal.
Yeah, but for the off diagonal part also it is universal. Yeah.
It doesn't matter what part of the things.
No, it does not matter. I'll show you. So the beauty of this approach is that we have calculated Higgs plus jet, right? Now you keep the mass of Higgs varying, okay? And these are different phase point. So once I calculated Higgs plus jet, according to what I have described, I can readily get W plus jet or Z plus jet. Okay, so this is the what we propose actually. This is the proposal.
The bond.
Yeah, we factor out the bonds.
So that's why we found the color factors.
That is gone.
Quark and gluon.
That is gone. Yeah.
The 1 plus alpha is.
Exactly. So Born is
So now the bond.
Born is always factored out. Yeah. Okay. Okay. So this is as I said, this is very useful. And we have also calculated it explicitly. So this gives answer to Shankho's question. So W is a heavy particle. So how can I apply the helicity formalism there? Any massive particle, you can write it in terms of two massless particles. And then I can apply the spinor helicity formalism. No problem, right? Yeah. And we have done the explicit calculation for every helicity configurations, and we have found that what we have proposed is true. Okay. Similar is the for soft form. So once I know the result for Higgs plus jet, I get the result for W plus jet and Z plus jet free. Okay.
They will have a different helicity configurations, right?
Yes. Yes, that is a very good question. So for Higgs plus jet, Higgs is like
Scalar,
there is no polarization. For W or Z, they have three polarizations. So you have to sum up the polarization. That's it.
But that will also induce different helicity combinations for the gluons also, will not? Then?
No.
They will not.
You sum up all the polarizations of W and Z. That's it.
This is at the cross section level.
Yeah.
Then it's that information is gone.
Unpolarized.
No, these are polarized cross section because helicity is intact here. I have not summed up the cross sections because, as you know, different helicity does not talk at the amplitude square level, right?
Some of the polarized.
That is the final state for the.
Sum of the polarization of the massive particle.
Polarized.
Sure.
Unpolarized for the color particle.
Polarized for the massive.
Polarized for the colorless massive particle.
Shotojit, the statement that the particles with different amplitudes do not speak to each other at the amplitude level, like yes, at the square level, but like at the decay level, they do talk to each other, right? Like when say for example the Higgs that you are talking about, if it decays to fermions, then these different amplitude squares would talk to each other, right?
How?
Because we would be talking about, say, in the terms of BB bar instead of Higgs.
BB bar is massive particle and there they talk.
Yeah, there
like
they would talk.
QT bar.
Yeah, exactly.
Right. I mean, for them, helicity is not a good quantum.
Yeah, so like till the point that we are at the Higgs level undecayed, we can make this statement.
Still we are dealing with the massless particle, the massless colored particles, we are saying.
True, and B is not one of them.
Yeah,
like we
right.
cannot do that. Yeah. Okay.
Okay. So for simplification of the calculation, I took this effective vortex, right? Now, what if I expand it and take the full theory? Will the same formalism work there? So that is under progress actually. And as you know, any one loop calculations, you can write it in terms of box, triangle, bubble, and rational term. So one loop is a completely solved problem numerically. So these coefficients you can calculate numerically. And these scalar parts, they are known, okay, in the literature. But the problem is that they suffer from numerical instabilities at the corner of phase space. Okay. So the way out is either you increase the precision in your numerical calculation, or you find a better way to express them analytically. Okay. And one of the approach to express them analytically is the unitarity approach. For example, glue going to Higgs.
So
Yeah.
what are the reason for this numerical instabilities?
If you go at the corner of a space, like very small momenta here and there, then it will give you some numerical instabilities, right?
So the I mean it's
region. If you parameterize the momenta such a way that it goes to the collinear region, then you will get numerical instability. Of
so
course.
is that coming from the solution from of the reduction?
Reduction means which
Tensor reduction.
Here there is no reduction. I mean, at this level, after reduction, this has.
Yeah. So all these coefficients are coming from the tensor reductions.
The coefficients are coming from the tensor reduction, but I am telling you that these coefficients you can calculate numerically. And their numerical instabilities come.
So the solutions are like not exist on those regions, or maybe blows up in those regions.
Solution is that you increase the numerical precision, right?
I mean, if the solution has the problem, even if you increase the numerical precision, how can you get the like particular solutions? I mean, let's say like in the reduction, if you do the Passerine-Nobelman reduction.
This is not Passerine-Nobelman, first of all.
I mean, what about the reduction?
Terms does not appear.
It can appear from the UV pole.
This format, this rational term. You can map, of course, but in the standard approach, it does not come actually, the rational term.
I think the statement is that whenever you're doing numerical calculation, you will always have
some instabilities, yes.
Space.
Exactly.
It's always known, right?
Is it because of the gram determinants? Like when one divides, like there are many reasons. Yeah.
Depending on what you're doing.
Cancellations as well, like numerical cancellations.
Yeah, exactly. Okay. So unitarity is one of the approach to get the amplitude analytically. Now, here the idea is you cut two propagators and you calculate the left part and right part at the tree level. Okay. Now, in this example, it is quite simple. But for the process we are interested in, that is, at the non-radiative case, it is Higgs plus 3 gluon, right? Now I cut two propagator, and if I calculate the left hand side, right hand side is easy. But if I calculate the left hand side, this is the expression, which is very ugly. Okay. Now, as Dirac mentioned at some point, it is more important to have beauty in one's equation. This is really disappointing. But he also told that if you are receptive and humble, mathematics will lead you by the hand. And that is also true, actually. So the same formula you can express in this compact form. Okay. And here also the savior is the BCFW. Here are the details, but I'm not going into the details. But using BCFW, you can write the amplitudes in very compact form. In fact, For TT bar going to n gluon, Ochiro presented the more general formula. You can by hand calculate 3 and 4, but for n gluon, it is quite a challenging task, but he did it actually. Okay. Now, as you know the compact form of these amplitudes, you can easily calculate the one loop amplitude, and this is the result, which is very compact. Sorry?
MHV.
Yeah.
They did not use any BCFW.
But
that was a conventional method, but still the answer was one line actually.
Exactly. But if you look at their I was looking at some point that is too complicated, but somehow they managed to find out that simple formula actually. There are many calculations in between. Yeah. Because of that reason, people forced to think that if the final expression is so simple, why the intermediate steps are so complicated? Yeah. No, this is the full amplitude. Yeah. And this is very compact. How compact? Let me show you some example. So look at the coefficient of this triangle. Now, people calculated this triangle coefficient earlier also. Okay, and this is their code. This plus this, which is just this term. Okay. And if you play smart with the kinematics of your problem, you can get such nice result actually. And once you know, once you get confidence in doing these calculations, even you can calculate for Higgs plus 5 gluon, which is inseparable part of calculating Higgs plus state at NNL. This is at one loop level. Yeah, exactly. And we implemented this in the code, the available code, MCFM, and we found that the code is now 5 times faster than the previous. Okay. Okay. There is a dictionary. From 4-dimensional helicity, you can go to any other canonical approach actually. Yeah. So you calculate the amplitude in 4 dimension and you do the integration at the n dimension. Yeah. Yeah. That is one approach. No, they will not give any other epsilon term, but they can give some finite terms. Yeah. Exactly. Yeah. Basically, you will not miss anything. From FTH, if you go to CDR, there is a dictionary. And the epsilon dependent part is always same in these two approaches. Yeah. Yeah, once you do the cut, everything is now tree level, right? Okay. I get your confusion. Okay. So, here in this example, I calculate the left hand side, which is tree level. I calculate the right hand side, which is tree level. Then I glue them up. Okay. So, when I cut, basically cutting a propagator means I am putting a delta function. Now I remove the delta function and put the propagator back. Then it is loop calculation again, right? That is what I am doing. But the expressions you have are for the cut part. No. This C0. C0 is the full, the triangle, scalar triangle, right? But if you have the expression for the cut part, you're saying like take the one loop out of that is it's trivial. Yes, right. Okay. Fine. Now this is again, so for what I have explained so far, is for all plus LCTs and gluon. Now for if minus LCT combines with them, then only BCFW would not save you to get compact result. You have to use momentum twister. You have to use, you have to take the help of numerics. You have to make the connection between scalar theory and Fermion theory. And also you have to use the higher finiteness. But I am not going into the details of any of this. Okay. Now let's check what we have explained for the NLP calculation, whether that is working in this one loop example as well. So say this 4 gluon is soft. Now, as the expression is simple, I can do the calculation in this slide only. So this term will be 0. Okay. Anything coming with 4, that will be 0, right? So these all are 0 at the leading power, remember. And this gives you this term, which is finally the iconal factor times the amplitude where one gluon is less. So this is working at the leading power. Now, what happens at the next to leading power? In next to leading power, you cannot put this term 0 directly, right? So, and this is one order less, I mean one particle less amplitude. So the idea is if I shift 1 and 3, I should get this amplitude. That is what I have described so far, right? But if you do the calculation, you will not get the complete term, right? You get something extra. But remember, there is 2 cyclic permutation in this result. And if you add these 2 cyclic permutations, that your term is this. And if you make shift now at 1 and 3, it is giving the result which is expected. Okay. So the cyclic property is lost, but the method is working, at least for the rational part. Okay. This is still under investigation. We have not published this paper yet. So the summary is that shifting of spinors captures the next to soft gluon contribution at the amplitude level, which makes the calculation very simple. And there is a one-to-one correspondence in the color in the radiative amplitude. The number of colored amplitude is equal to the number of colored dipoles in the non-radiative amplitude, right? And the starting point then is always non-radiative helicity amplitude, which is always simpler. When one particle is less, the amplitude would be simpler, of course. Okay. And for Higgs plus jet, we have shown that no NMHV contribution coming in the at the NLP level, and also making twice of the dipole D12, giving you full result. Also, we have studied the soft quark contribution, which is simpler. The method is generic, and we can apply it for any number of jet in the final state. Also, we have studied the universality of the logs, the coefficient of the logs. And it is interesting to test this formally for loop induced process, which I have already described briefly. And this is basically the founding steps for NLP resummation for the jet associated processes. So the immediate future plan is that I have to study the NLP effects for the loop amplitudes. I have to include the collinear effects in this and the angular ordering, I mean the Chudakov factor, which is called, whether that is holding in this case or not at the NLP level. Basically, all these will make you able to construct the NLP correction. Okay. And the formation of amplitude level subtraction key based on this, because these NLP terms, they are basically the power corrections. And based on that, you can make a subtraction scheme as well. Okay, so these are my immediate future plan, which I want to finish within 1 or 2 years. This is my list of publications where you can see that I have worked on NLP, fixed order calculation, matching with pattern shower, NNLO, resummation, slicing, and there are a few more, not reading all the things. There are 2 preprints on NLP corrections, one of which has recently got accepted the day before yesterday in PRD letter. Okay, now these are my future plan for the next 2 to 3 years. I want to develop the subtraction scheme using method of regions. I have been discussing with Ratan for quite some time regarding this. the improvement of non-local slicing approach, because there are some subtleties in the n-jettinase or the QT subtraction. The n-jettinase works for plus jet production, but it has huge power corrections. Whether QT does not work good for jet production, but its power correction is less. So whether there is a way to work them both at the plus jet level. Okay. Investigation of the algebraic structure of elliptic polylog, mixed QCD electroic corrections for processes with massive legs, and then I want to include the NLP effects in the pattern shower. As of now, pattern shower, the effect of LP is included up to certain level, NNLL. But I want to include it, the NLP effects in the pattern shower. And also, recently, which draws my attention is that there is some nice paper by Matthew Schwartz, who is simplifying this helicity amplitude using machine learning. So I want to explore that part maybe later at some point. Okay. So probably I have convinced you through my talk that this precision QCD calculations, they are not only important, they are inevitable. And if you find the beauty in these calculations, you will understand more the world of elementary particle physics. Thank you.
This approach you can apply to study, let's say, the kind of thing, string theory study, you know, graviton scatterings,
yeah,
and stuff like that actually.
Actually, this soft theorem, came from the graviton side only. This is Strominger paper, the famous Strominger paper.
Yeah.
There they first describe these things.
So they study this soft factor in the graviton.
Yeah.
This next to soft part in the context of gravitons, is it easy to study in this way actually?
Yeah, it is easy actually.
And you can make some statements about universal structure.
That's the calculations, because that spinor structure is something different than the, I mean, there is a tensor structure, right? H mu nu will come in the graviton side. There I have not applied it, but I am sure that as it came from the graviton side, it can be applied.
I think the
People
first
did it for the graviton side first, and then people go to the QCD. So we have to go the other way.
it was done from that side, like from gravity side. Then Ashok and the Vishwajit, they actually, without using this, just by using string theory, I guess.
So some years ago, I remember reading. Yeah.
With Vishwajit Shah, yeah, right.
No, I don't know whether he used CFW, but he correct. He has actually done the calculation. Because we were also looking at it in the context of thermal field theory and
some
I do not understand
memory theory or something, right?
Oh, stick field theory. Yeah, correct. That's right. What about the higher order loops? Would it be as easy to cut them to get these real? I mean, one loop I can always cut to get two real
that
parts,
is
but
not generalized yet.
not generalized, right?
For maximal cut, it is working. But for less than that,
what do you mean by maximal cut?
You can cut all the propagators.
Oh, right. Okay, that way. No, but suppose you have things like overlapping divergences and all. Where do you cut?
They're really difficult.
You cannot even figure out how to start cutting it, right? So,
true.
I see. Okay, thanks.
So
very interesting.
The examples that you showed were for like Higgs plus jet or W plus jet or Z plus jet. So so basically like a heavy particle plus several massless particles. So is this like, can this be generalized to like multiple heavy particles plus?
Sorry, can this
so like generalized, like will these results hold for like say 2 Higgs plus jet? So any of these, so everything will go through exactly like this. So the bond part can be just factored out.
Exactly.
Difficulties with the massless ones.
Difficulties with the massless, the colored particles actually.
So like if the quarks, for instance, are bottom quarks and we are in a lower energy regime, then like also, around the Higgs threshold or something.
Then also I don't know what will happen. because in that case maybe one have to redo the calculation, the BCFW part.
Right.
Yeah.
So all these calculations, like when you showed this Q, capital Q plus X, so these are either light quarks or in a high energy limit.